Hi, in this video, we want to take a look at a very simple initial linear regression model. All right, so this is a linear regression course, and we're going to start with a linear regression with one variable predicting another variable. We're going to call the variables that are used for predicting the predictor variables, and we're going to use the target variable or the dependent variable called the target variable. That's a pretty standard machine learning terminology. All right, so this is taken from the class textbook, A Modern Approach to Regression with R. Here I'm focusing on the code, not the actual text from the book, because you can just read the book. Now, this book is available to download for free by all UCF students through the library's website. All right, so when I get going, first thing I'm going to do for this example is I'm going to set my digits to be displayed at 2 significant digits. I do this just to truncate the output so I don't get overwhelmed with numbers. At work, normally I have it set at 5. I think 5 is the default. But whenever I'm doing a document, a video, I'm going to set the digits to 2 or 3 to make sure I don't put on, just basically vomit a bunch of stuff onto the page. All right. The first thing we need to do, we need to load the data. All right, loading the data, in my experience, is the toughest step for almost every student in statistics. If you can get the data into the system initially, usually students can take things the rest of the way. But loading the data inside R or SAS or Python or whatever, there tends to be some difficulties. R is probably the most persnickety of the ones to load data in. I strongly advise you to load your data the way that I load my data. If you're using RStudio, RStudio has features where you can just click your mouse, click, and load it in. I'm going to tell you right now from the get-go, don't do it. Don't do it. Do it with the code. Why is that? You're going to be working on your project. You're going to be doing things. You're going to change your mind on what you're doing because you're going to have some serious code, some serious stuff to work on in this class. And you're going to be like, oh, well, I was doing this. I want to like redo it, start over. Well, you use your code to automate the redoing of it. You don't have to remember what you did because you wrote it down in your code. One of the functions that our code does for us when we're doing our statistics is it tells us what we did, and it makes it so that we can reproduce what we did very easy, very quickly. All right, so what I'm going to do, I need to get the file path of my data sets. And in Windows, it's file.path, then choose.files, or file.choose, either way. And what it will do, it will give me this character string. Now, this character string for the file, well, basically, after I type this in to the command line, this part right there, a GUI is going to pop up, and it's going to show me where my files are. I'm going to click around to find where my data set is. I click on my data set, press enter, and what's going to happen is it's going to give me this character string right here. So I can see that in the C folder, in the user folders, in my NID folder, in my desktop folder, and so on, all the way down, there is a TXT file called production, and that's the data set I want for this example. This entire string tells R where is that file stored. I strongly recommend that you go about loading your data in this manner. Now, when I read in the data, I need to use a function that is specified to the type of file I want to pull in. This is a TXT file. So usually with TXT files, we want read.table. It's not 100% guaranteed, but most of the time. If you have trouble, just let me know in Canvas and attach your file, your data set on there is like if it's a CSV or whatever, and I can help you out. Now, some data sets will have headers, some will not. What a header is it's the names of all my variables at the very top row. If I have this set to false, it's going to assume that very first row is data. If I set header equals true, it's going to say, hey, that the first row are column names. and that's the header of the data set. So that's why we call it header, and we set equal to true. Okay, so after I load this, so here's my data set, and you'll notice that I called it production, and I use this arrow and then the minus sign, well, I guess it's less than and then minus to make it arrow, and that's how I am declaring that production is the output of this function. And we can see if we scroll down, we have 20 observations in the production data set. All right, well, something we normally want to do, we want to do univariate statistics, is that we want to go through and we just want to get the summary of our data. So case, we can look down here, we can just see that case is, it's not a meaningful statistic. It's just, what row number are we talking about? We can see that runtime is the amount of time it took, and run size is the size of the run. So we would expect that if we were going to get a larger size of something to run with, it would take longer to process. Now, I don't know what this data set is recording, what these measurement values are. For our purpose on this video, we don't really care. Now, when I get into the real world, we don't want to have that willy-nilly attitude. I want to understand each and every column. And here we can see, here is the average, the mean. Here's the median for each of, for each row or each column of data. And we can get the first quartile, third quartile, min and max. All right, it's without like a frame of reference, doesn't really tell us much, but it's something there. All right, so let's go ahead and let's do a scatter plot. So here's what I want to do. My hypothesis is that runtime depends on the size of the stuff that I'm working on, my run size. So my hypothesis is as runtime changes, as run size changes, runtime will change also. And I'll go ahead and say that as one increases, the other increases, one decreases, the other decreases. That's my belief. So as a first initial go, let's go ahead and do a scatter plot. Now, this just tells R to have one row and one column of subplots. It doesn't really, it's not important for this example. Probably could have skipped that. But here for my plot, I'm going to say that my predictor variable is the X. I'm going to say that my target variable is the Y. And I go ahead and just label just to make sure that when I look at it, I know what I'm looking at. So let's go ahead and look. All right, so as we can see, as run size increases, we can see that, the Y value increases also. But I mean, it's not a perfect fit. It's not a perfect straight line. But I mean, overall, if it seems reasonable, we'll go ahead and go with it. All right, so let's go ahead. What I want to do, I want to fit a linear regression line to this scatter plot, to these data points. So what we're going to do in R, we're going to use the LM function, which stands for linear model. So what I'm going to do, I'm going to pass a formula. So here we're saying that runtime depends on run size. So I have the target variable, and then I have the predictor variable. And you notice I have this tilde in between. The tilde says depends on. Runtime depends on run size. And then I specify what the data set is. Okay, so now let's go ahead and put that line onto that scatter plot that we just looked at. So this part of the code is the same. We already did this. This is what gave us the scatter plot. Now I'm using AB line to specify a line to put on there. So if I put reg equals the linear model that I built previously, so here linear model production is the regression object I'm working on. And I'm going to go ahead and make it red to make it different from the dots. And boom, we see that. And yeah, okay. I'll go ahead and accept that there's a linear model. Honestly, this is spread out enough that it's not really the, I wouldn't really want to use it for predictions if I was doing like a machine learning problem, but maybe for inference, if I want to see how, on average, how much does time increase by size? Yeah. All right, so this is a statistics class, which means we're going to be doing hypothesis testing. Hypothesis testing is a critical aspect of small data and medium data analytics. All right, so the big bread and butter hypothesis testing and regression is going to be the Anova test, and it's going to be checking to see if the coefficients are statistically significant. The coefficients are going to be a big deal, as we'll see as the semester progresses. Here we've got Anova. All right, so analysis of variance. What we're going to do is, remember, Anova is a ratio of variances. Anova takes the F distribution and gives us an F value. Well, what is the F test? Do we remember the F test? The F test comes from the ratio of variances. So what we're doing is we're taking our sum of squareds here. So here's the sum of squares, and then we're dividing by the degrees of freedom to get this value. Divide the sum of squares by the degrees of freedom to get this value. And so here, in a sense, these are a variation. We take the ratio of these two, we get 48.7. And then from here, we look up on the F table from your introductory to statistics class. Remember, I have two parameters for degrees of freedom. It's going to be degrees of freedom 1, degrees of freedom 18. If you go in and check, you go back to your introductory statistics textbook, go to the back of the book, you find the F table, you look up 1 and 18 degrees of freedom, you find 48.7 or something close, and you're going to see it is super close to 0. It's going to be very, very small. All right, so what does the Anova test tell us? The Anova test tells us that there is informative value in the predictor variables. Right, let me repeat that. The Anova test tells us that there is informative value in the predictor variables. Okay, so in this example, we only have one predictor variable, but down the road, we might have like 10. And what Anova tells us is that somewhere in there, we don't know where, somewhere in those predictor variables, there is some informative value that we would like to keep. Now, I only have one variable for this case, so that's not a big deal. If I have 10 predictor variables, some of them might be worth keeping, some of them I want to throw out. Anova just says at least one of those predictors is useful, keep it. It doesn't tell us which one or ones, it just says something in there is a gem, keep the gem. Okay, well, if we run summary on our model, we'll get some more information. I'm going to take a moment. I'm going to back up for a second. I want to point out one of my conventions when I do my coding. Do you notice that every single time I call a function, I declare what the item is? So I've got the object is equal to linear model production. When I'm up here, when I did that plot, I said that X is equal to this, Y is equal to this, X lab is equal to this, Y lab is equal to this. Now, it is super, super common for people who do programming to put like the first item in, second item in, third, without specifying what they are. And that will work just fine. What you will find is, 6 months down the road, when you have to go back to your code, like you do when you work professionally. So when I'm at work and I have to go back to my code, if I don't specify, if I was to just put, production run size, comma, production run time in here without specifying X and Y, it wouldn't be clear to me exactly what the object is inside the function. So I'll be confused. I won't know what's going on. And I have to go look it up, and that will slow me down, and I'll already be frustrated because looking at your old code is never fun. But I mean, at work, you end up doing it anyway. So you'll notice that when I do my summary call, I say, what object do I want to summarize? And I want the linear model. All right, so let's take a look. So it gives us the call. So if I printed this, I can look and see, how is it that I got the code to run? Now here's the residuals. The residuals are the deviation between the model and our observed values. Now, the mean will always be 0 for this type of model. If I'm doing simple linear regression, if I'm doing multiple linear regression, the mean will always be 0. Okay, so there's no point in listing the mean. But here they've got the box plot values. Remember, a box plot is a 5-number summary. I've got the minimum, I've got the maximum, I've got the quartiles, and I've got the median. So it gives me an idea of what's going on. And really, I want to see that the deviation from here to here is about the same as the deviation from here to here. I want the deviation from here to here to be about the deviation from here to there, in magnitude. We'll talk about residuals a lot in this class. All right, now here's our coefficients. So here's the estimated Y-intercept. Here's the estimated run size. Okay, so what this model is telling me is that if my run size is 0, then I'm expecting the time to take 150 of time. Now, that might make sense because maybe there's an overhead aspect, maybe like a booting up of a machine, warming up a machine, something like that. We don't know. Now here, we can see that we've got, I'm just gonna say 0.3 is my run size coefficient. All right, so what I'm expecting, if I increase run size by 1, I'm expecting a run time increase of 0.3. And now when I say expect, that's on average, I expect to see a 0.3 increase for each increase of 1 to run size. All right, so that gives me a magnitude idea of how big increasing the size will be. Now, here is the standard error for the estimate of the Y-intercept. And here is the standard error of the run size coefficient estimate. Okay, so think of standard error in the same way as you do standard deviation, but it's like specific to a statistic instead of like a regular data. Okay, so if I take the estimate and I divide by the standard error, I get the t-value. If I take the estimate, divide by the standard error, I get the t-value. Just like in your introductory to statistics course, what you would do after that, you would go to the back of your book, you would look up, all right, so my degrees of freedom, and then I would look up the t-value, and then I would use the t-value, degrees of freedom, to get my p-value. Now, software will give me a much more precise number, so I can see that's darn small. That's negative 13 exponent. That's teeny tiny. So we can be pretty confident that the intercept does not equal 0. Now for run size, we can see that we've got about 2 times 10 to the negative 6. That's still very, very tiny, not as tiny as the intercept. So here we are pretty sure that the coefficient is not equal to 0, under our hypothesis test. The summary commands also give us these little stars to indicate what's going on. So if I don't see any stars, if I don't see any, then the p-value is between 0.1 and 1. If I see just a dot, it's between 0.05 and 0.1. If I see 1 star, it's between 0.01 and 0.05. If I see 2 stars, it's between 0.01 and 0.001. And if I see 3 stars, like we have here, the p-value is less than 0.001. Now here this tells us our degrees of freedom. So I will use this when I go to look up our p-value on the t-table. Now we're not going to be using t-tables at all, but I want you to think back to that time, remember, of looking stuff up. We're going to use software to just spit it out at us, which is going to be a better way to go. But you always want to be thinking about that process to know, where do these numbers come from? Now here's my multiple r squared. Here's the adjusted r squared. When I'm looking at models, one of the things I always want to do, if adjusted r squared and multiple r squared kind of move away from each other, if there's a big gap, adjusted r squared will be less. If there's a big difference between them, I worry about overfitting the model. We'll talk about that more. And here's our F statistic. All right, so now let's double check. Let's see, did we actually get the same values that I'm claiming? Well, if I take the estimate and then I divide by the standard error, I took these values and it gave me 18. Now remember, I went ahead and rounded off the values and I got 18, and that is right at 18. If I take the runtime estimate and standard error, do division, we get 7 after rounding. Boom, that's the same. Now, we're not going to compute the p-values here just because we haven't talked about what are the degrees of freedom on the intercept and the run size coefficient, but we'll get to that. I know you're excited. All right, now let's take a look at confidence intervals. We're in a statistics class, so we're going to be doing hypothesis tests and we're going to be doing confidence intervals. All right, so if I want to do a confidence interval on my coefficients, I just use the command confint for confidence interval. I say what object I'm putting in, and I put the level, and it's automatically going to spit out the confidence interval for the intercept, 95% confidence interval. And you know, we can see that the 2.5% lower bound and 97.5% upper bound. And you can see that 0 is not in there. Now the run size, we can see that it's between, let's say, 0.2 and 0.35. Something like that. And you'll notice that when I'm looking at numbers, I tend to round them off to make them easier for me to interpret. If I have a whole string of digits and I think of it as 0.346289112, then it's not humanly possible, or not possible for me to really understand that, and the digits get in the way of interpretation, and that's a problem. All right, so I've built this model. In real life, when I do a model, either I want to get inference or I want to get predictions. Let's go ahead and start looking at predictions. So what I want to be able to do is, let's say someone comes up to me and they're going to go ahead and they are going to use a run size of, let's say, 68. And from the 68, they want to know on average what will be the runtime. Well, what I can do is I'm going to take the 68, I'm going to put it into my model, and it's going to give me a value. And that will be my prediction. So what we want to do, I need to get a new data set. So for this situation, I'm building what's called the score data. The data that we make predictions on is called the score data. The data that we build models on is called the training data. So score data is what I actually want to make predictions on. Training data is what I build the model on. All right, so here what we're doing, I'm taking a sequence of values from the smallest run size to the maximum run size, and I'm doing a step of 5 every single time. And I'm making a new data frame where those steps I'm calling the run size variable. And here is the output of it. So I go 58, 63, 68, 73, 78, 83. You'll notice it's steps of 5 because I put by equals 5. Okay, so now if I put this into my model, what will the predictions be? So I can see that if I was going to do a run size of 58, we would expect it to take 165 for time. If I do a run size of 63, it would be I would expect the runtime to be 166. If I do a run size of 83, I expect the runtime to be 171. All right, so these values are actually representing 2 different numbers. One is the predicted value, one is the expected value. Okay, so in linear regression, prediction and expected value are the same thing. So the predicted values are these, but also the expected value. So on average, if I put in a run size of 68, I expect to see on average a runtime of 167. All right, well, I mean, that's something interesting to know. So if we know like the size of the runs are going to be coming in. Let's say I'm running a factory, I'm a manager, and I know how frequently different sizes come in. I can go through and try to predict how long it's going to take for each of them to make a more efficient process and improve profits. Okay, so those are the point estimates. Now, you know, in statistics, we don't ever just leave it at point estimate. You know that if I have a point estimate, I want like some kind of interval around it. Well, remember, I said that we had two purposes of this. We have the expected value, what's the expected time it's going to take, and I have the predicted time it's going to take. So we're going to get two different intervals. One is the confidence interval for the expected value confidence interval. One is the prediction interval for the width of the prediction. All right, so when I do, what I'm going to do, I'm going to take the predict function. I'm going to set the object equal to my linear regression model. My data is the score data. Now, interval is going to be a confidence interval. When I say confidence interval, this is saying I'm interested in the average. I'm not interested in the prediction. I want the average. So this is going to give me the interval around the predictions. Sorry, around the expected value. And then I want to know my level. All right, so here we can see that we've got a confidence interval for 165 is 151 to 178. The confidence interval for 171 is 159 to 183. So I am 95% confident that when the run size is 171, the true average runtime is between these two values. Now let's talk about the prediction interval. Okay, first thing I want you to notice, check out 128 and 202. Compare that to 151, 178. You notice that both times it's for 165. Compare these values. Which one has the lesser lower bound? That one's lesser, right? Which one has the greater upper bound? That one's bigger, right? Okay, so what we can see right away is that our prediction intervals are wider than our confidence intervals. Prediction intervals are here, confidence intervals are here. Why is that? Well, what's going on is that this is trying to tell us what is the average. We're trying to nail down the average. If you remember from back in the day in your introductory statistics course, your standard error decreased for sample averages. It was much smaller. Your standard error was much smaller than this population standard deviation. This is trying to estimate the width for the average. And the average, it will always have like lesser variance, lesser standard deviation. When I get down here, this is trying to give me an interval for 95% of the observations I'm going to see. This is the interval that I expect 95% of observations to be in. This is my 95% confidence interval for the average. There is a difference. Now to get this, the code is the same as we did before, except I set interval equal to prediction. All right, so now let's go ahead and plot this so we can get a better idea of what's going on. So this part is the same as before, but now I'm going to put on the confidence interval, and I'm going to put that in blue, and then I'm going to put the prediction interval in purple. Now let's look and see. Okay, so how do I interpret this? I want to look at this vertically. Look at it vertically. So let's say I'm interested in 250. If I go up to 250, the model says that the average, if the model is correct, the average will be here, which is, let's just say 210, something like that. Now, my confidence interval for the average is the blue lines. And remember, I have to go vertically. Go vertically when you look at this. All right, so my 95% confidence interval is between the blue lines. Now, my prediction interval is here. So here, if I was to run 250 run size over and over and over and over, we would expect the observations, the observed runtime, 95% of them to be between the purple vertically. All right, that's all I've got for you. I hope you're doing well. Take care and goodbye.